Now, so these are two benzoxy radicals. So I will just repeat. We have formation of radicals. One, this we have already discussed. The generation of chlorine radical, generation of chlorine radical by photochemical reaction, which we have already discussed. And this chlorine radical, this can induce the radical formation of methyl radical. See here, chlorine radical can do the job. Next, yeah, you can generate, the chlorine radical can react with methane and form a methyl radical. So one radical can be used to form another radical. Another method of initiating radical reaction is use of hydrogen peroxide, H2O2. H2O2. You can get the H2O2 from common market, from medical shops, you know that. So it's a very common material. So we have H2O2 here, and that will undergo thermolysis, the homolysis. The O bond is highly energetic. You have to just supply a little light. It will get broken into two hydroxyl radicals. Similarly, you can form peroxides. Here is peroxide. Two alkyl peroxides. You can have methyl peroxide, dimethyl peroxide, CH3, oxygen, CH3. So this is nothing but dimethyl peroxide. Similarly, you can have diphenyl peroxide or dibenzyl peroxide. So only thing is you have that OO bond which can be very easily broken. Okay. So that is then you can do the same. You can form other radicals by thermolysis. Thermolysis by application of heat. So thermal homolysis. You can say this is thermal homolysis. Homolysis means, you know what is homolysis. That is breakage of two bonds to form radicals to either side. This is what is called homolysis. Okay. That under thermal condition you can do this. Similarly, you can have this. This is this is carbon. Let me correct it. You people also will write the same way, even if I remember it is carbon, but you may forget it. I don't want to happen that. Correct yourself if anybody has written oxygen here. Similarly, here also it is CO bond. This is oxygen. This is carbon. Okay, so don't make mistakes. Because my pen, I am not able to, sometimes it will just get some overlap. I correct everything. Otherwise, I know you people will simply draw something and just without understanding. This is CO glue, a carbonyl glue. You have a carbon here. Okay, so this is formation of benzoyl peroxide. Okay, now let's look at the hybridization of this molecule. Look at the hybridization. Structure, stability, and hybridization. So let us write hybridization. Hybridization of radicals, free radicals. Free radicals. Hybridization of free radicals. I have already explained to you last time. You have the carbon in the center. You have three hybridized orbitals. One is in this plane. The other one is this plane. All these things we have already discussed in one of the YouTube videos. You remember that? Now here is this for third bond, a carbon here, a hydrogen here, and then you have an orbital which is in a perpendicular direction and contains one electron, one odd electron. Okay, one odd electron. And see here, this bond angle. See, this is on to the back side. This is to the front towards you, and this is in the plane of the board. And therefore, this bond angle should be ideally 120. Remember that. This bond angle should be 120 degree. This bond angle is also 120. And this is also 120. Now, suppose you rotate this along this axis, 120. Suppose you rotate this along this axis, 90 degree out of plane. This will look like this. See here. So this is 120. This is 120, and this is 120. And how will this orbital look like? See here, this orbital. It is rotated. That means you are looking from here. Now you are looking from this side. So it will look like, see here, like this. In a perpendicular plane. Okay. So that is the geometry of the molecule. You have three hydrogen which are sp2, two hybridized, and they are okay. They are in a perpendicular plane here. So it is the orbital containing the odd electron is perpendicular plane to the other three hydrogen CH bonds or CR bond. It can be R also, right? So that is a radical hybridization. And now, quite naturally, this will be a trigonal planar. It will be trigonal planar. Remember, when we talk about the geometry, we will be talking only on the hybridized bonds. We have three sp2 hybridized CH or CR bond. So they will be CH bonds, they will be trigonal planar. Now let us look at the stability of these free radicals. Stability. Okay, let's think about the stability of this one. Now the stability is in this order: CH3, CH, CH3. Oh, which control of C, CH3. Oh, sorry, one extra CH. So this is a secondary one. Then you have a tertiary radical. Tertiary radical. C which is not. One CH3, another CH3, another CH3. Right. Many of you will get confused afterwards. That's why I have to write CH3. Okay. Now, you can have CH2, CH3. That is ethyl radical. So this is less stable, more stable than CH3 radical. Remember, this electron is in the carbon, with the carbon. So with this, you can say methyl free radical. Methyl free radical. FR stands for free radical. Please complete it. This is ethyl free radical. It's also primary. This is a secondary isopropyl. And this is T-butyl free radical. T-butyl. Now I have noted, see here I have written, it is stable due to two effects. That is, tertiary is more stable than secondary, more stable than primary, more stable than methyl free radical. Now, there are two reasons for it. Number one, what you call as inductive. How does inductive effect play out? And what is inductive effect? I will just write. Did we? I think we haven't mentioned what is inductive effect, but you already know. When you have a bond, the electrons are more closer towards a more electronegative atom. That is inductive effect. In the case of CCl bond, this is the inductive. Okay, here is the inductive. So here the electrons are away from the carbon. Here the electrons are towards the carbon. So we have this you call as minus I effect. Plus I effect. That is, electron is gained by the carbon, and this is minus I effect. Electron is lost by the carbon. Electron is lost by the carbon, slightly towards the chloride. So the electron is flowing away from electropositive element towards electronegative element. So this is electronegative element, more electronegative. Oh, how many people are coming now? What is this? Is it that you are not getting the connection? Now, don't use that as an excuse for being late, please. I don't have any objection of you people coming late, but still, that doesn't look good. If you're not getting, genuinely you're not getting connection, it's okay. Okay, it doesn't matter. We have the excuse due to corona. So many corona excuses, right? Anyway, now see here, you have SECl bond. This is more electronegative. Let me write it here. You also write it. More electronegative. Electronegative atom. More electronegative atom. Please write all this in your book. This is less electronegative atom. So it is coming closer, hence closer to the chlorine. Hence, electron is closer to the chlorine. Electron is closer. Here, this is more electronegative. Carbon is more electronegative. Carbon more electronegative. More electronegative. Then what? Then hydrogen. So electron is the pair of electron is more attracted towards the carbon. So electron is gained by slightly electronic charge is gained by carbon. Now look here. So when you have a CH3 group, when you have a CH3 group, who's now coming? Shamna. Okay, when you have CH3 group, you will have, look at the CH3 group, CH, H, H, and H. See here. Electrons are closer to the carbon. Electrons are closer to the carbon. From all the three hydrogen, electrons are closer. So you will get delta, I'll put delta, 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 3 delta negative. Here it is delta positive. Very slight positive charge here. This is delta positive. This also is delta positive. So what is the cumulative effect of this? Accumulated effect. The three effects are accumulated, and therefore this carbon become more the carbon become quite electronegative. That is more electron dense due to the flow of electrons from this hydrogen towards the chlorine, towards the carbon. So one CH3 group, a CH3 group is electron donating due to this effect. So if you have a CH3 group, see here, CCH3, I can write this is slightly delta, delta negative, delta negative due to the electropositive character of hydrogen. So therefore, if you have a bond, carbon is having another bond with another atom, the electron can flow in this direction. See that? So this is electron dense and electron rich. So we will write electron rich. Electron rich. So electron can flow from here to the next element. Suppose you have a chlorine here. See, suppose you have a chlorine here, or you have a carbon here next to it, and then a chlorine. See the flow of electron. So these electrons are flowing towards this carbon, and suppose you have more and more CH3 groups. More and more CH3 groups. See what happens from all the sides. From this CH3 group, electron coming towards this carbon. Electron is coming towards this carbon. So this will become more and more electronegative, electron rich, and that electron richness will flow towards this chlorine. And chlorine is ready to accept it. Remember that. Why chlorine is ready to accept? It is more electronegative. More electronegative. More electronegative. So this chlorine will always be ready to accept the electron from here. So what is the net effect? What is the net effect on the structure? See, I'll write it very clearly here in a big picture. See here, this is the net effect. More the number of methyl groups. Oh, sorry, my writing sometimes I lose the control. More the number of methyl groups. Clearly, let me write it. See, flow of electron towards this carbon, towards this carbon. See, and that increases the electron density here. So if this is a radical, sorry. Now if there is a chance for electron to flow towards this carbon. Okay, so there is a chance of flow of electron towards this carbon, right? So what will happen? The electron density will be increased by the electron density can be increased, will be increased by the inductive effect, and that will destabilize, increases electron density, electron density, electron density. Now, increase of electron density, what will happen? Increase of electron density, decreases stability, decreases stability. So, stability. So, inductive effect is supposed to decrease the stability of tertiary carbocation. So, if you consider only inductive effect, if you consider, oh, otherwise coming just now, or if he has already got disconnected, let's see. And now, see here. Now, see here. This, so increase of electron density will decrease the stability, and therefore, if you only consider the inductive effect, if we consider only inductive effect, effect. Then now which is more stable? Tertiary will be less stable than secondary, less stable than primary, and less stable than methyl radical. Now let me underline this. Don't get misguided. If we are considering, oh, Renisha, no, now within another 5 minutes, I think we'll have to stop the class. Yeah. Now, if we consider only minus I effect, okay. Now, can we continue even if it is getting cut? Can we continue for another 20 minutes more? Okay, I will rejoin. Will you be ready? Will all of you be ready? I have got about 9 people now. There were more than 9 people, but some of them have already gone. I got 9 people now. Are you ready to continue for another 20 minutes more? Okay, right. Okay. Anyway, I will start it again. After once this is closed, I will start it again. This will automatically stop. So I will restart my Zoom again. So those who are present, please join again. Okay. Now let's continue. Now see here. So if we consider only minus inductive effect, then if we consider only inductive tertiary radical, tertiary free radical, secondary free radical, primary free radical, and methyl free radical, the order of stability is increases in this direction. Increase in order of stability. Increase in order of stability means what? Tertiary is least stable. Tertiary is least stable. Least stable. And primary is most stable. So this is the consideration. When you consider inductive effect, this is the order of stability. Now let us look at another effect. What is called hyperconjugative effect. I will explain to you what is hyperconjugative effect based on this only. Look here, hyperconjugative effect. Hyperconjugative effect. Hyperconjugative effect is a flow of electron through sigma bond. How? Sigma bonds of hydrogen atom. Okay, look here what happens. Look very carefully, try to understand very carefully. Look very carefully and try to understand it. See, you have, let me draw a methyl radical. Sorry, let me draw a methyl radical. Okay, see here, this is, oh, let me draw everything very clearly. I will repeat it for use a pen control. Using the pen control. Okay. Now this is a methyl radical. I'll only write a methyl radical. H here. H here. H here. And see here, these orbitals, these electron and these electron, they are in mutually perpendicular bonds. I will draw this, the complete picture of this. See here. Here is the electron with the orbital with one electron.